Welcome to This Explainer. Today, we're totally demystifying vectors, turning them from those confusing little arrows on a page into a simple, completely predictable language of movement. Look, if you've ever stared down a Cambridge IGCSE math paper, especially the 0580 syllabus, and felt totally overwhelmed by all those bold letters and grid lines, you are in exactly the right place. Today, we're going to break this topic down systematically so you can absolutely crush those exam questions. Here's our game plan for today. First, the language of movement. Then, combining vector paths, followed by scaling and reversing, measuring magnitude, and finally, cracking vector geometry. All right, step one, the language of movement. Let's start with the absolute basics. I want you to think of yourself as a translator, decoding physical movement onto a mathematical grid. Forget about complex formulas for a second. At its heart, vector math is just a way of giving extremely precise directions. Okay, let's dive into this. A translation simply tells you how many steps left or right, and then up or down it takes to get from point A to point B. We write this as a column vector. It kind of looks like a fraction, but without that line in the middle. The golden rule here is so simple. The top number is always your horizontal movement along the x-axis, and the bottom number is your vertical movement along the y-axis. Take vector AB, for example. That top number, 1, tells us to move 1 step horizontally to the right. The bottom number, 3, tells us to move 3 steps vertically upward. It's really straightforward. Positive numbers mean right and up, while negative numbers mean left and down. Once you can read that column, you can map literally any straight line movement in the world. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, step 2, combining vector paths. Now that you can translate a single vector, what happens when we combine them by placing these movements tip to tail? Because let's be real, we rarely travel in just one straight line. We take multiple paths to reach a final destination. This brilliantly illustrates how vector addition is literally just simple arithmetic. You just add the top x values together and the bottom y values together. Vector A takes us 2 right and 5 up. Vector B takes us 3 left because it's a -3 and 2 up. If we follow path A and then path B, our total journey is found by just adding them up. 2 plus -3 gives us an x value of -1, and 5 plus 2 gives us a y value of 7. So our final direct path from start to finish is simply -1, 7. It's incredibly logical. Step 3, scaling and reversing vectors. Next up, we need to figure out how to change a vector's size or make it travel backward along its path. Because sometimes we don't want to add entirely new paths, we just want to modify the one we're already on. Contrast a positive movement with a negative one. If vector A means moving right and up, negative A means moving exactly the same distance but left and down. Reversing your directions simply flips the mathematical signs. So +2 becomes a -2, and a +5 becomes a -5. You're walking the exact same line, just heading back home to where you started. Multiplying by a scalar just scales the vector, meaning you multiply both the x and y numbers by that scalar, stretching or shrinking the physical path. If vector A is -2, 4, then 2a means we just do that exact same movement twice. -2 times 2 is -4. 4 times 2 is 8. If we want half the journey, say 1/2 a, we just cut those coordinates right in half, giving us -1, 2. The direction stays perfectly consistent, only the distance changes. Step 4, measuring vector magnitude. Okay, so we know how to move and combine paths, but how do we measure the exact physical length of that movement? We've talked about how to move left, right, up, and down, but what if you need a tape measure to find the exact length of that diagonal arrow drawn on your grid? Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, getting back to magnitude. Finding it might sound terrifying, but honestly, it's just our old friend Pythagoras' theorem applied to a new situation on a grid. Because the x movement is perfectly horizontal and the y movement is perfectly vertical, they form a right-angled triangle. Your vector arrow is literally just the hypotenuse. Let's move to a quick example and see how this builds. Squaring the 3 and the 4 gives us 9 plus 16, which is 25. Then we just take the square root. We're just squaring the horizontal distance, adding the squared vertical distance, and preparing to take the root. which means the exact length or magnitude of that vector path is precisely 5. By the way, the magnitude of a vector is always represented by placing straight vertical lines around the letter, kind of like the absolute value symbol. So whenever you see that specific notation on your Cambridge exam, don't panic, just think Pythagoras. Step 5. Cracking vector geometry. Armed with all our tools, we are now totally ready to tackle complex spatial puzzles without getting overwhelmed. This is where a lot of students get stuck, but because we've built such a solid foundation, you're going to see how straightforward this actually is. So here's the crucial point. A vector isn't locked to one spot. It's a set of instructions that can slide anywhere around a geometric shape. If a vector tells you to move 3 steps right and 2 steps up, it doesn't matter where you start on the page. Any line that is parallel and the exact same length represents the exact same vector. This is your absolute superpower for vector geometry. Let's test this logic on a classic hexagon puzzle you might see in the source material. How do we get from point A to point B using only the known paths A and B? Imagine you're in a maze and you can't walk directly from A to B. You have to use the defined paths that already exist in the diagram. We know the path from the center G to A is A, and the center G to B is B. We just follow the physical path backward along A, making it negative, and then forward along B, giving us our final combined expression. To get from A to B, we first walk from A to the center G. Since G to A is vector A to G is walking that path in reverse, which we now know is negative A. Then from the center G, we walk down the normal path B to reach point B. Combine them, and your answer is simply negative A plus B, which is usually written much more neatly as B minus A. See? Just follow the roads. This leads right into the most advanced challenge in the syllabus, proving relationships between entirely separate lines. In an exam, you might be asked to prove that line PQ is parallel to line MN, and that one is a multiple of the other. If you can prove that one vector is just a scaled-up version of another, like BC equals 4 times DE, you've mathematically proven they are perfectly parallel. The logic behind this is so cool. If 2 lines have the exact same ratio of x to y movements, meaning one is just a scalar multiple of the other, they absolutely must be pointing in the exact same direction. The number on the outside, the scalar, just tells you the difference in their magnitude. Proving this unlocks the highest marks on a vector geometry paper for sure. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. As the quote says, vectors are simply a universal language describing physical movement. From translating a simple column vector to cracking a regular hexagon, you've successfully learned how to fluently translate the language of movement. You now know how to combine paths tip to tail, how to stretch or reverse them, how to measure their physical length with Pythagoras, and how to slide them around shapes to solve complex geometric proofs. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCS and click that bell. Don't let another exam pass you by. So, to leave you with one final thought, if a vector tells you exactly how to move, what mathematical concept tells you where you started? Think about how position vectors anchor this movement to a specific origin. That's something I invite you to explore next time as you continue mastering your exams. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.